So why is it that spinning an object around like this is simpler than spinning an object around like this? Today we're going to have a look at vertical circular motion. There's no difference in terms of the equations, you already know everything that you need to know, but we're just going to look at some of the extra detail today that makes vertical circles that little bit more challenging. At the start of the video I asked you to do what I like to affectionately call a lift problem. It's about a lift. They're really common. I think every year there's a lift in there somewhere. You drew a force diagram, and that force diagram had a tension going upwards and a weight going downwards. You knew that the weight was 200 G because that's what's given in the question, W equals mg, and it asked you to calculate the tension. What equation did you use in order to calculate that? If you said F equals ma, you're only half right. Anyone who knows me from my lessons will know that I hate F. F shouldn't be there. Because F is not an actual force. F is the resultant of, in this case, the tension and the weight. You don't use F equals ma, you use T minus W equals ma. Those people who are in my classes will know that because I made a really big deal of it this year. Gary and Tim's classes, I can forgive you so long as you got it right. Always write in the forces instead of F, because it just makes life easier. And it's this idea of the resultant force that we're really going to cling on to today. And force diagrams are the number one way to understand mechanics and what's going on. I got you to define centripetal force just to really lead you into that final question. What does the lift problem have to do with circular motion? Well, the equation for centripetal force, mv squared over r, comes from F equals ma. The centripetal force is a resultant force, just like the lift problem, just like the F in F equals ma. And in certain cases, we don't want to be using that F at all. If our object is moving in a vertical circle, we want to be using the forces that are acting on it, not F. When I spin my lanyard in a circle, can't really slow it down very much, otherwise it doesn't work. At the bottom, the tension provided in the string is acting upwards, and the weight is acting downwards. If I wanted this to be moving into a circle, we'd need a centripetal force mv squared over r. At the bottom of the circle, the resultant force on my lanyard, you're just going to have to picture it spinning, and I've frozen time. The centripetal force on my lanyard will be T minus W, because those two forces are opposing each other. T minus W equals mv squared over r. And so, we could solve this to find the tension or to find the weight. We could work out, we could just solve it for whatever we need. At the top, however, pause time again, the tension and the weight are in the same direction. So the resultant force on my lanyard, mv squared over r, will be T plus W. And so my equation to use will be T plus W, tension plus weight. They're acting in the same direction, they're going to add up to provide that centripetal force. At the side, for reasons best left unknown, at the side you only need to account for the tension. Okay, I know that the lanyard will have a weight, but at the side we only need a tension. In exams, you just need the tension at the sides, T this way. So at the bottom, T minus W, tension's acting up, weight's acting downwards. At the sides, and this side as well, tension is the only force that provides the centripetal force. At the top, acting in the same direction, T plus W equals mv squared over r. Do you get how that works? The only reason why it's more complicated is you need to take like a microsecond to think about the direction of those arrows. That's it. Are the forces opposing each other? Are they acting in the same direction? Are they at 90 degrees to each other? Do they subtract? Do they just have one of them? Do they add up? Those are the only three key situations that you'll be asked to think about as well. They don't complicate it by saying, oh, what about over here? What about over there? It's only ever bottom, top, middle, or the middle. If you look at the exercise in the book where it has a roller coaster, it's not a tension this time. The upwards force is going to be the contact reaction force from the track. And again, it just looks at those 4 key situations, at the bottom, at either side, and at the top. I want you to add to this diagram, where you've drawn it, I would like you to add reaction force up, call it R, weight down, call it W. And I want you to write R minus W equals mv squared over R, because that will be the equation that you use there. At the sides, I want you just to write R equals mv squared over R, and that will have to be a capital R for the force, for the reaction force, and a little r for the radius. At the top, where you've sketched it, I would like you to write R plus W equals mv squared over R, because at the top, they're both going to add up to provide that resultant force towards the centre of the circle. Do you notice that? And it's only ever going to be one of those 4 situations. How do you know which one? Draw it. If you're ever worried about how to add up, how to calculate forces in mechanics, draw a force diagram. So think about your mechanics, draw your force diagram. If those forces are in the same direction towards the centre of the circle, add them up. If they're in the opposite direction, subtract them off. And set that equal to mv squared over r. Because after all, the centripetal force is the resultant force, and that is why. Forget the F and use the forces themselves, T minus W, R minus W. Write that and set it equal to MA, or in this case, mv squared over R. So if you look at the examples there, on the roller coaster example, once you've drawn those things, at the bottom of the loop, it just tells you what acceleration they want. In the first one, you're just plugging in the numbers to find V. So you know the acceleration is 6g, you know the radius is 8 meters, so you just plug in those numbers, you get V. And once you know V, in this case, I think in the booklet they use N for normal reaction force, going upwards, weight going downwards, then rearrange that equation to say that the normal reaction force has to be mv squared over r plus weight. And that's where that equation comes from. It's dead easy. All you're going to be doing today is using that idea of F equals ma and the fact that F is actually 2 forces rather than just 1 to solve circular motion problems. That's it. But this is the harder part. It takes more practice. In example 4, you've got to realise that eventually that normal reaction force is going to go to 0. The normal reaction force can't pull you back to Earth. It can only ever push back. So the maximum speed will occur when there's only one force, when the weight is the force pulling the car over the bridge. And that's how you arrive at that equation, V equals root GR, which I like to affectionately call the speed bump equation, because that's how you design speed bumps. Sometimes you get those limiting situations where one of those forces goes to 0, but again, really, problems like question 4, they're just problem-solving questions, realising how the physics works. The more you practice from the back, the better you will be. I'm going to finish with the standard answers. First standard answer, these are actually in the middle of the book. The first standard answer asked, why does the speed remain constant even though there is a resultant force? Surely, if there's a resultant force, the speed should increase. Work done is force times distance moved in the direction of the force. You know that in order to do work on an object, your force and your distance must be at least partly in the same direction. You also know that if the force and the distance moved are at right angles to each other, no work is done. And if you look at the relationship between force and velocity, between force and distance moved at any point on the circle, they are always at right angles. The velocity is always at right angles to the force. Therefore, no work is done because the force and distance moved are always at right angles. Therefore, the kinetic energy remains constant. No energy transferred. It's quite simple, isn't it? Much simpler than trying to argue it any other way. Learn that the work done is 0 because the force is at right angle to the distance moved, and therefore the kinetic energy is constant. The next question is just a recap of all of those conditions. In order for an object to move in a circle at a constant speed, it requires a resultant centripetal force acting towards the centre of the circle at all times, at right angles to the velocity. You'll see this throughout physics, everywhere from particle physics, electric fields, gravitation. Wherever there is a force acting at right angles to velocity, you get circular motion. That is the only condition that is required. Before we finish, I would like to add my own standard answer to this book. It's one that will help you probably in the end of topic questions. The question is, what if I remove the centripetal force? What happens to the direction of motion? When you remove the centripetal force completely, the object will continue in a straight line with constant velocity. Whenever there's no resultant force acting on an object, it will either remain at rest, which isn't the case here, or moving at constant velocity unless it's acted on by resultant external force. Whose law is that? That's Newton's first law. So when I remove that resultant external force, the velocity remains constant and it continues just moving at right angles to wherever it was. It just keeps moving in a straight line. It does not change direction. That's a really important little thing to bear in mind that's not written in the book, just an extra little piece of information. Write that in on a free page. There's a bit of space towards the back of the book. I hope that that's a handy summary of vertical circular motion in vertical circles, and I can't really say more. Practice them, get to know them, realise what's going on. If you've got any questions, email me and ask.